Dear students, now I am going to discuss magnetic dipole moment of a current loop. A current carrying loop has a dipole, that is, it acts as a dipole. It has got one end behaves like a north pole and the other face of a loop behaves like a south pole. Suppose the current in the loop is say like this, clockwise, this way, clockwise current. Okay, so then we can assume or we can say the loop behaves like north pole. So current is clockwise. Current is clockwise. So this phase of the loop, in which side we are seeing it as a current is clockwise, then that phase of the loop, current loop, behaves like a south pole. Okay, south pole. So here see the letters yes. Ends I have shown here, yes. And if the current is in a loop, is anti-clockwise. This is a current loop. Current is anti-clockwise. So the current is flowing this way. That is anti-clockwise direction. So current in a loop is anti-clockwise. Anti-clockwise. That phase of the loop behaves like a north pole. Okay, so how we can show this, or how we can remember this? Like this. Okay, so this behaves like a north. Say arrow mark here, this arrow mark at this end. Here also, n letter end of the end here, and this arrow mark going inside. Okay, so this way we can easily remember this. So if the current in a loop is clockwise, and that phase of the loop for us it looks like south pole, and if the current is anti-clockwise, that end of the loop behaves like a north pole. And for a dipole, there will be dipole moment. Like an electric charge, have dipole, means a small positive charge and a negative charge separated by a small distance, q and minus q, separated by a small distance 2a, constitute electric dipole, and the dipole moment P equal to 2a into q. So here also, if there is a current I, okay, there is a current I in the loop. Okay, so dipole moment, magnetic dipole moment of a current loop, magnetic dipole moment M of a current loop is denoted by symbol M, that M equal to, okay, I into A. I means current, A is area. Okay, so I is electric current through a loop and A is the area of the loop. Okay, that is area. Now SI unit. This is for a loop. Okay, if it is a loop. If it is a coil of n turns, for a coil of n turns, the dipole moment of the coil is NIA. Okay, NIA, where n is number of turns. How many turns are there in the coil? Number of turns in the coil. So NIA. Now we have to find what is the SI unit and dimensions. So SI unit of current, okay, SI unit of M. SI unit of M is, current SI unit is ampere. Then area, A stands for area of the loop. If it is circular loop, then it is pi r square. Rectangular loop, length into breadth. So area SI unit is meter square. So this is the SI unit of dipole moment. And N has no dimension or no unit, number of turns. In this coil or it is a loop, then the unit of magnetic dipole moment is ampere meter square. Electric dipole moment, just recall, coulomb into meter is the dipole moment. Charge Q into 2a. Okay, magnet of either of the charge multiplied by the distance between the two charges. Here the dipole moment of a loop is current flowing in the loop multiplied by area of the loop. Okay, current into area, that quantity is called as the dipole moment. Okay, so AM square is the unit. And then, okay, dimensions or dimensional formula of this M, dipole moment M is, okay, what is the dimension of current A? Is A only. A is the dimension of current. Then area is L square. So A L square is the dimensional formula or dimensions of the dipole moment. Okay, dimensions. Next comes the torque in a torque acting on the dipole. Okay, torque expression, torque on a current loop or coil when placed in magnetic field, when placed in uniform magnetic field. If you take a current loop, uniform magnetic field. Okay. Now let us take a current loop, current carrying loop. A loop is carrying a current I. Okay. Then it is placed in an external magnetic field. So remember two things. One is the current carrying in a loop means it will produce a magnetic field. And we are placing such a loop which is producing magnetic field, which is producing its own magnetic field. Such a loop is placed in an external magnetic field. External magnetic field means field produced by some other source, not because of this loop. So this is also producing a magnetic field. This is also producing magnetic field because there is a current. Whenever there is a current, there is a magnetic field. Okay, so whenever current is flowing in a conductor or a loop, there will be magnetic field produced around it. Now such loop is placed in an external magnetic field means that field is produced by some other source. Now this loop, whenever placed in an external source produced by external magnetic field, so it will experience a torque. Okay, so the torque experienced by that loop. Okay, let me show the diagram here. So this is the direction of the field. External magnetic field B vector. And now if I place a loop, okay, whose area vector I will show like this. Okay, area vector of this loop is this way. So direction of area vector, vectorially I can write M vector equal to I into A vector. Area is a vector, remember. Okay, so M vector has the same direction as area vector. Area is normal outward. So current here is flowing like this. So dipole moment here outward. Okay, so the area vector is outward. Here current is clockwise. Okay, current is clockwise. The dipole moment is inwards. Here dipole moment vector M vector is outward. In this case N current is anti-clockwise. Okay, M vector outward direction. Okay, whereas here M vector in case of south pole clockwise current, M vector is a normal inwards. See, in the direction of current I have to curve the fingers. In the direction of current is clockwise. Okay, so when I curve, the thumb points inward. So the direction of thumb shows the direction of, so normal inwards. The direction of the dipole moment. It is a vector quantity which is magnitude as well as direction. So vector quantities we use by represented by arrowhead with the one line with the line segment and arrow. So now this okay, so such a loop or a coil also can be placed in an external magnetic field, external uniform magnetic field. So uniform magnetic field lines, the lines are parallel and equidistant, and the loop is placed in such a magnetic field. It experiences a torque, and the torque is given by torque tau equal to M cross B. Okay, M cross B. Torque experienced by the loop whenever a current carrying loop is placed in an external magnetic field. It experiences a torque whose torque experience is given by vector expression. It is M cross product with the B vector. Okay, M vector cross product with B vector. And the magnitude of torque is MB sin theta. So this we studied already in the first year itself. A cross B is AB sin theta. Magnitude is AB sin theta or MB sin theta n cap. One unit vector you have to assign to show the direction of torque. Okay. So now this is the torque experienced MB sin theta, magnitude of torque, and vectorially torque experienced by the loop is M cross B. Tau vector equal to M vector cross product. It is not multiplication, it is a cross product with the B vector. Okay, so this is the magnitude of torque, and SI unit of torque is, see, it is Newton meter. SI unit of torque is Newton meter. Okay, SI unit of torque, okay, is Newton meter. Okay, so it is equivalent to joule. And dimensional formula is the same as dimensions. Okay, it is m l square t power minus 2. m l square t power minus 2. That's it. That's about the dimensions of the torque. Fine. Now maximum torque, minimum torque. Say, look at the expression here, mv sin theta. Magnitude of torque is maximum when sin theta is 1, because sin theta value maximum is 1. Maximum value of sin theta is 1 when theta equal to 90 degree. So first case, when theta equal to 90 degree, sin theta is 1, tau is maximum, tau max equal to mv, sin theta is 1. And same way, second case, when theta equal to 0 degree or 180 degree, theta equal to 0 degree or 180 degree. Okay, so sin theta is 0. Sin theta is 0. When sin theta is 0, torque is minimum in magnitude. Okay, torque is 0. So question can be, when will be the torque experienced by a current carrying loop placed in an external magnetic field is maximum? You have to say theta equal to 90 degree. So what is the significance theta equal to 90 degree? The angle between area vector and b vector. Area is taken normal to the plane of the loop. Okay. Suppose the field lines you assume like this and a loop is placed this way. So the direction of this loop is normally I would take like this. It is a normal outward from the plane of the loop. Okay. So if this is the surface, if I take normal, I have to take the direction of area vector of this surface is normal to the surface, and the normal to the surface and magnetic field direction. So that angle is theta. That angle is theta. So that's the idea. So area vector is normal outward from the loop. Angle between A and B is 90 means this is the field direction. The loop must be placed this way. So that is theta is 0. So minimum torque this situation. And maximum torque is like this. The surface is in the direction of the field. The surface or loop, current carrying loop is placed in the along the field direction. Then theta equal to, say theta for this case, area vector normal to this way and field is this way, right side. So what happens? Angle between area vector, this is magnetic field, and area vector outward, so that angle is 90 degree. So the theta 90, you can also say the magnetic field B is perpendicular to the area vector or the plane of the loop, plane of the current carrying loop is along the direction of the field. In that case, what happens? Plane of the loop in the field means area vector is perpendicular to plane of loop. So area vector or dipole moment vector, because area vector and dipole moment will have same direction. Okay, so area vector perpendicular to B vector or dipole moment of the loop and the magnetic field will be perpendicular. So that's all about this idea. So minimum torque is when theta equal to 0 or 180 degree. That means the situation when the field is like this and the loop is this way. So that area vector is parallel to B. Area vector is parallel to B, theta 0. So that the torque experienced by the loop is minimum, it does not rotate. So the function of this torque, or what does this torque makes in the loop? So it will rotate the loop. Because of the torque, the loop will rotate or it will change the orientation. So that's all about this torque part, dipole moment and torque experienced by the loop. Next we go to the important topic here. Sometimes it can be asked as 5 marks question. Okay, so that is the magnetic dipole moment of electron. Okay, so magnetic dipole moment of revolving electron. Magnetic dipole moment of revolving electron in hydrogen atom. Electron. Okay, so the electron is revolving inside in the hydrogen atom around the nucleus. Okay, so consider such an arrangement. So this is the nucleus here. Okay, this is the nucleus with the charge plus E. Okay. nucleus means it is a proton. Now an electron is revolving around it like this, okay, in a circular path. Okay, so it is according to Bohr's theory we are doing. So it is revolving around the nucleus in circular path like this. Okay. Yes. The electron is revolving around the nucleus in circular path. So this is the electron here. Okay. The radius of the orbit I will take as r, and the direction of velocity vector is this way, v vector. Direction of velocity is v. Okay. Now what you have to do is we have to find out the dipole moment of this revolving electron. Okay, revolving electron dipole moment we have to find out. So there are two charges. So revolution, electrons are revolving around the nucleus because of the centripetal force is provided by the electrostatic force given by Coulomb's law. Okay. So now the electron, whenever it is revolving in a circular path, okay, so that is carrying a charge. The current due to electron motion we have to assume opposite. Okay. So the current due to electron motion is equal to current due to electron motion around the nucleus. We have to take it is E, current 1 revolution. Whenever charge moves 1 revolution, the magnet of charge mode is E, because magnet of electron charge is E. Actual electron charge is minus E, but magnet of electron charge is plus E. Okay. So E by time period. So in 1 revolution, whenever electron completes 1 revolution, it makes a large number of revolutions in 1 second. Frequency is very high. Okay, so it will move like this, and the charge moved in 1 revolution is E, and the time taken is T. T is time period of revolution. Okay, so where E is magnitude of electron charge, and T is time period of revolution. Okay, then what happens next? So we have I equal to E by T. Okay, now what is the time period of revolution? So time period of revolution in connection with its velocity of electron. So we can say magnitude of velocity. Okay, magnitude of velocity V equal to distance travelled in 1 revolution. Electron travels a distance equal to circumference 2 pi r divided by time t. Okay, so which implies t equal to bring a t to the LHS and take v that side. So 2 pi r by v. So this is the time period t equal to 2 pi r upon v. Now using this in 1. Okay, so this is a 2 and this is 1. So what I do, substitute using equation 2 in equation 1. Using equation 2 in equation 1, what happens? So current I equal to E divided by denominator is time period t. So simple it is, magnitude of velocity I have taken. Velocity is a vector, so I said magnitude whenever electron moves. Distance traveled 2 pi r, and the time period is t. Time taken for 1 revolution is t. Now substitute. Okay, here it is 2 pi r divided by v. So this becomes EV by 2 pi r. Okay, E into V, small v, divided by 2 pi r. Okay, so this is the current. So the current I due to electron motion is EV divided by 2 pi r. Okay, this is the equation for current. Okay, now equation number 3 I take. Now what happens whenever electron is revolving? The magnetic dipole moment of electron. Okay, so magnetic dipole moment. By definition of dipole moment, so that is it is like a current loop now. Electron is moving in a circular path means it is like a current loop. Okay, so dipole moment of revolving electron is I denote the symbol mu. So mu equal to, okay, magnitude I write, vectorial I write later. So mu equal to current I into area. Current due to electron motion multiplied by area of the loop. Okay, so now substituting. So I equal to, we got it, EV by 2 pi r. EV by 2 pi r is current I into area of the circular loop due to electron motion. So Bohr assumed that electrons are evolving in a circular path, even though electrons are not always circular paths. It can be elliptical path. and oriented in different orbits. Okay, so but the special case assumed by Bohr's is that electrons are moving in circular path. So EV by 2 pi r multiplied by area. Area is pi r square. Okay, area is pi r square. Now, so mu equal to, what happens you see, r square by r cancel, 1 r remains, pi cancel. So what it remains here, EV. Numerator and this pi and pi you can cancel, pi cancel, and this r cancels. So it remains EVR divided by 2. EVR divided by 2. Now I can multiply numerator and denominator by mass of electron. So that I write as EVR divided by 2m, okay, 2me into me. Okay. So then I can also write mu equal to, okay, I will take here E as constant out, E by 2me, okay, then into E by 2me out, MEVR, okay, MEVR. Me stands for mass of electron. Okay, so now there is a reason for multiplying, dividing Me. So when I multiply and divide Me, so this, what is MEVR or MVR? Product MVR is nothing but angular momentum, orbital angular momentum here it is. So in both postulates you have seen, angular momentum of electron revolving in the any stationary orbit is integral multiple of h by 2 pi. That you have studied in both second postulate. Okay, so E by 2me into MEVR. So this MEVR is a quantity called the angular momentum of the revolving electron in the hydrogen atom. So this is a hydrogen atom, not any other atom, hydrogen atom. So mu equal to E by 2me. This E by me is a constant, it is always constant for a given electron. Okay, so E by 2me into, so this is L, okay, and vectorially mu vector equal to electron dipole moment equal to minus E by 2me into L vector. Okay. So there is a symbol minus now. What this minus is? The dipole moment vector and the L vector, angular momentum vector, are opposite. The dipole moment of the electron is opposite to the angular momentum. So see, whenever it is electron is revolving, the angular momentum direction L vector is equal to r cross p. It is r cross p, r vector, then p vector this way. So dipole moment, angular momentum vector L vector is normal outward. It is the cross product actually. Angular momentum L equal to r cross p. Okay, that is equal to r cross mv. So mv, cross product. Cross product means vector product of two vectors. Okay, so it is a vector quantity. Whereas scalar product or dot product is scalar quantity, no direction for that. Whereas this L vector, angular momentum, is a vector product of r vector and p vector, momentum p. Okay, r is radius here. So r cross p, direction of r cross p. So momentum is along the velocity, radius is this way. So the direction you see, the direction of angular momentum L vector is outward, normal outward. Okay, so whereas mu L is inward. Mu L vector is inward, so that I write here. This stands for mu L vector. Okay, dipole moment of electron is inward. X mark indicates mu L vector. Dipole moment vector is inwards. I use by L here, subscript L. So mu L vector, vectorially, magnetic dipole moment of revolving electron in hydrogen atom is minus E by 2me times L vector, that is angular momentum of the revolving electron. Magnitude of angular momentum is MEVR. Okay, it is a vector quantity. So this is about the derivation, and here I have defined two terms. One is gyromagnetic ratio, another one is Bohr magneton. Gyromagnetic ratio means the ratio of dipole momentum to the angular momentum. Okay, so first term, yeah, this is about the derivation. Just briefly recall, first what you have to get, current I. Electron is moving in in a circular path, revolving in a circular path around the positively charged nucleus. So current I equal to E by time period. Magnitude of charge moving in one revolution is E divided by the time period. Then velocity equal to radius circumference upon time period. So we get time period, rearrange. V and T, we rearrange and we get T equal to pi r by V. Substitute here for the denominator, that is T equal to, here denominator T is 2 pi r by V, so EV by 2 pi r. Then to get dipole moment, just multiply current and area. So EV by 2 pi r, cancelling pi and R, we get EVR by 2. Then we want a dipole moment in terms of angular momentum. So multiply ME divided by ME. Multiplying ME and dividing by ME. So nothing will happen. Same number, mass of electron is multiplied. Then numerator becomes MEVR, E into MEVR. This MEVR quantity is called the angular momentum, magnitude of angular momentum. Whereas ME, E by 2ME is a constant. Okay. So now I define gyromagnetic ratio. Gyromagnetic ratio. Okay, so gyromagnetic ratio means the ratio of, it is the ratio of what? Magnetic dipole moment of electron to the magnetic dipole moment. Dipole moment of electron to the angular momentum. Angular momentum. This is called as gyromagnetic ratio. That is mu L by L. Magnitude of dipole moment divided by magnitude of angular momentum. So that is equal to, if you bring this L to the LHS, what happens? Here only, bring L to the LHS, E by 2ME. E by 2ME. Okay. Now substituting the values, E is 1.602 into 10 power minus 19 divided by 2 into mass of electron is 9.11 into 10 power minus 31 kg. That becomes, okay, when you calculate 0.88 it comes, okay, 18 point, okay. So the value is 8.8 into 10 power 10 coulomb per kg. Okay, so coulomb per kg. So actually when you calculate 1.602 divided by 2 and divided by 9.11, it becomes 0.088. 0.088 and 10 power will be plus 12. Okay. Now 0.088 into 10 power 12, I write it as 8.8, but I write 10 power 10, that's it. And unit will be coulomb per kg, because coulomb is the unit of charge, coulomb here, and this is mass kg, correct? So unit of gyromagnetic ratio is coulomb per kg. Coulomb per kg. That's all about the gyromagnetic ratio. Okay. So then next comes the Bohr magneton. Bohr magneton. Last one definition is there. Very important definition. Bohr magneton. Bohr magneton means the minimum value of magnetic dipole moment of electron. Okay. So minimum value. So I have here mu L minimum. Okay, mu L minimum. Okay, that is called as Bohr magneton. So mu L equal to E by 2ME into L. Now we know from Bohr's postulate, Bohr's second postulate of quantization, what we know? We know that L, dipole angular momentum of electron L is mvr equal to MEVR is NH by 2 pi. Okay, NH by 2 pi, correct? So this we can recall from the chemistry. In chemistry you studied Bohr's second postulate. Now MVR equal to NH by 2 pi or L value. So mu L equal to E by 2ME 2 into mass of electron into NH by 2 pi. Okay, NH by 2 pi. So this expression I can write NEH divided by 2ME into 2H. So that becomes 4 pi ME. 4 pi ME. Okay. Now minimum